Chris Richmond. Oh, yes, thank you. So today we have Chris Richmond, who's a professor. I think, did we start at the same time, or maybe you started one semester before me?
I started
Uh,
in January 2018.
right. Okay. So I started in fall 2018. Okay. So Chris has been great. He's just a couple of doors down. So he's been showing me the ropes at the very recent ropes at ASU, right? Like not like the really seasoned expert yet, but then he's been showing me ropes around ASU. Chris is an expert in statistical signal processing, information theory. He's been doing a lot of cool stuff on Kramer-Rao lower bounds and all that kind of interesting stuff. And especially we have had several conversations about how these things relate to when the models are not well known, and he's done some really nice work in those things as well. So I'm excited to have him talk today, and I will hand over the mic to you, Chris.
Thank you. And I'd like to thank Gautam and Lalitha for inviting me to give a talk in the seminar series. I'm going to talk about some work we've been doing on the subject of shared spectrum, and in particular, the coexistence of radar and communication systems, and share some recent results that we have, which we're pretty excited about. So what I'll do is I'll give sort of a short introduction on the topic for those who may not be familiar with sort of shared spectrum and what the objectives are. And we're going to focus on basically two main results. One is a bound on cooperative performance. And the other is basically a method for assessing the receiver operating characteristics for a radar that's cooperating with the comms. So a little bit about myself, folks who don't know me. I did my undergraduate in a dual degree engineering program at Bowie State University, which is a historically black college and university, and then went to the University of Maryland. And that turned out to be a really good move for me because by the time I took my first engineering course, I had already had like partial differential equations. So I was pretty well prepared for the engineering courses there. Then I went to MIT. That was great. And Lincoln Laboratory sort of picked me up as an RA. And so working there or going there right after grad school was a natural move for me. And it was fantastic. I really loved it. The people at Lincoln are amazingly talented. I got exposure to a wide spectrum of programs and problems. It was just great. I had a chance to teach for a couple of years at Harvard and really loved it. So I decided to pursue academia full time, and an opportunity opened here at ASU, and I came here as you heard in 2018. We've established the Signals Information Inference and Learning Group, or SIL for short, and our focus is basically the theory, application, and practice of statistical signal array processing. What we're trying to do is essentially advance technology for existing systems. It's typically for mostly DoD type systems that are already in place, but they want to improve capability, but also developing technology, advancing technologies for new emerging systems. And we do this through innovative algorithm designs, theory, analysis, and experimental validation when possible. So here's a list of all of our current research topics, and there's our website below, so please feel free to poke around there. If you see something interesting you'd like to talk about, collaborate with, feel free to get in touch with us. I'm going to share basically today what we've been doing on sort of shared spectrum RF convergence. All right, so what is shared spectrum? Well, most of you probably know that the way the FCC allocates spectrum is everybody has their own parking space and frequency, right? And so if you have basically more than one system, you say you stay in this spot and I stay in that spot, and we're all happy. So what I'm interested in this particular problem is basically how well a radar system and a comm system can coexist in the same frequency band. And for those of you who may not know, over the last, I would say 10, 15 years, the military and some civil organizations have actually sold off frequency bands that they've had for decades. So there have been people who have lobbied in Washington, D.C. and convinced the right folks to do this. And so, there's certain bands of frequency that were sold for something like $45 billion. And so some of that money has basically been given to organizations like NSF and others, and they're basically giving that money to folks like you and me to try to figure out how to do with half the frequency band they were doing with the full frequency band. Somehow they drunk that Kool-Aid. They really didn't talk to me. If they talked to me, I probably would have told them not to sell it in the first place. But that's what they're planning to do. So the money is being spent to try to figure out how we can improve spectral efficiency. And so we're considering the possibility of a radar coexisting in the same band as a comm system. And we're asking, here are these traditional ways of sort of breaking up the time and the frequency, just sort of having allocated spots. But the question we're asking is there a smarter way? Is there something we can do that's a little bit smarter than just sort of breaking up these bands? And part of the reason for, sort of considering this is, if you look at how much of the spectrum is actually being used, over a given year, just imagine it being like parking spaces in a parking lot. And if you observe those parking lots over the whole day, how many cars are actually in those spots? And what they found is that it was a large percentage of those parking spots that were just empty a large majority of the time. And so, if I have an assigned parking spot and I'm at work, then someone else can use my parking spot and it doesn't bother me at all. So there's got to be a more efficient way to sort of use the very limited spectrum available. And plus, nobody wants to give up bandwidth. Bandwidth translates, as you know, into increased data rate, translates into improved resolution for radar, translates into, more coherent integration gain, for target detection. So if we can get away without giving it up, that would be ideal. So that's what our objective is here. If I force a radar and a comm system to play in the same sandbox, which means they're stepping on top of each other, can I design these systems in a way that they step on top of each other in a smart way and everybody's happy at the end of the day? All right, so that's the goal, right? And so what I've been focusing on is asking some fundamental questions. The first question is, what's the theoretical bound? What's the theoretical bound for, the data rate that a comms link can achieve if there's a radar sitting in its band? What's the, rock performance or parameter estimation performance limits of a radar if a comm system is constantly in its band? And we want to ask that question, but we want to ask it in the context of two systems that are cooperating. So if there's information that could help me to coexist with the comms, then the comms is going to be willing to share the information. I'm going to be willing to share my information. All right. So we want to focus on what the theoretical bound is, and then two, we want to assess the performance of a radar receiver that's cooperating with the comms. All right. In particular, we're going to be interested in the rock performance, probability of detection versus signal to noise ratio, say for fixed probability of false alarm. All right, so that's sort of the problem. And I'll tell you first about the bound, and I'll tell you about what we have on rock performance. So first I want to just remind you, radar and a comm system are, very different systems, right? The goal of a comm system is transfer data from point A to point B. All right, that's the objective. A radar system has a multifaceted set of objectives. First, it wants to detect the target, then it may want to localize it, and then it may actually want to track it over time, right? So if you think about how you might formulate a cooperative system, right, the problem spaces for both of these systems are very different. They're very different. Why is that important? Because our first inclination is to write down a metric that we want to optimize over so that we can figure out what the right solution is. But I'm dealing with two systems that are very, very different. So coming up with a single metric takes a little bit of thought, right? So if we think about a comm system operating in isolation, a lot of my colleagues here know this very well, that, we know that the optimal data rate that you can push across a link is something that Claude Shannon basically laid out very clearly for us is given by the mutual information between my transmitted waveform and my received data at the comms, denoted here XC. And if I wanted to maximize my data rate so that I can decode with the lowest probability of error, I can basically just maximize this mutual information over the channel code word distribution. And that'll get me the maximal data rate, sometimes known as the channel capacity. All right, so that's the way, that's the limit of data transfer over communication. So that's the preferred metric. If we think about a radar, radars, they have, as I said, a more complicated mission. If you've never heard of the concept of radar, it stands for radio detection and ranging. And basically, the goal is usually long-range surveillance, right? And the way we do that is we transmit electromagnetic energy into our environment, and then we just wait for returns off of objects that we're looking for, right? And we exploit the motion of the platforms that the radar is on, as well as the motion of the targets to sort of help with that, both detection, tracking, and surveillance. All right, so let me tell you a little bit about the signal environment for the radar, just so you have some appreciation for some of the challenges that you have to deal with. Let's say this is my airborne radar, and so in my aircraft here, and I'm going to define my coordinate system relative to my platform, and my goal is to detect targets. So I'm going to do that by transmitting energy. Usually I use a phased array, so I focus the energy in a particular direction. Then I just rotate this phased array in 360 degrees around. So this transmit power pattern is basically designed to transmit energy in the direction I'm looking for power efficiency, right? And you can imagine this sort of power pattern just rotating like the minute hand around a clock. That energy goes out, bounces off of the target I'm interested in. I'll transmit a waveform that I know, and then I'll look for those returns. And when that waveform comes back, it's been altered in certain ways. It has a time delay that tells me something about how far away the target is, and there's a shift in the carrier frequency known as the Doppler that gives me some idea of the closing velocity or the exiting velocity, how far it's moving, how fast it's moving away from me. When I transmit energy, it bounces off of things I'm looking for, but it also bounces off of things I'm not looking for. All right, so that produces what we call ground clutter. It's a self-induced interference. It's sort of, part of the course. It comes with the technology, right, or this approach. So we have to have a way of dealing with that clutter, because that could easily blind our ability to detect the target. And radars transmit at very, very high powers. So you're not going to hide the fact that you're transmitting a signal as a radar, right? So if somebody doesn't like the fact that you're performing surveillance, or they just kind of want to make life difficult for you, they could put a signal in your band and cause you problems, make it very difficult for you to detect the target you're looking for, right? And we call those jammers or interferences, but my goal is to detect the target, but here's the challenge. This is the challenging environment in which you have to do that detection, right? So we want our signal processing to embrace all of these possibilities. All right, and so here's a typical signal processing chain for radar. Typically, our first goal is detection. Once we detect something, we want to say, hey, what did I detect? Is it a target? Is it some bright scatter on the ground, perhaps that I'm not interested in? We want to classify it. If it's something of interest, we may want to localize it and track it over time. All right, and we basically accomplish this through signal processing. So in terms of the cooperation between a radar and a comms, I kind of want to focus on one of these, aspects: detection, classification, localization, and tracking. All right, so I'm going to focus on detection. Basically, just to sort of get started, I'm just trying to understand how well these two systems can coexist and perform what they want to do. So my analysis in terms of my bounds and my Rockwell form is going to be focused on the detection phase. But most of what I'm going to share today in terms of the bounds can be applied to classification, localization, and tracking with a slight modification of some of the performance metrics we introduced. All right. So let me say one thing about the radar performance. Hopefully this is familiar to most of you. Target detection is very easily described as what we call a binary hypothesis testing problem. The radar measures some data, and if there's no target there, then we say that data consists of just noise only. When I say noise, I mean colored noise, so it has clutter, interference, jamming, all of that's in there. But when there's a target, I have noise plus the target return, right? And VT is my the component that is contributing from my target. And as a goal, as the goal of detection, my objective is to find a decision rule so that when you give me a data measurement, the output of this decision rule is either a 1 or a 0. It says 1 if I'm going to say, yes, there's a target there. That's hypothesis H1, or 0 if there's no target there. That's the goal of my the design of my detector, is to find this decision. Typically, the way we do that is we make some assumption about the distribution of the data under each hypothesis, and we use that information to try to define an optimal detector. If you study this, you know that the Neiman-Pearson criteria is one of the popular choices here. Basically, what it does is it introduces this essentially Lagrangian that consists of the probability of detection plus some constraint on my probability of false alarm. And my goal is to design my decision rule, phi, so that I maximize this Lagrangian. So maximizing probability of detection subject to a constraint on my probability of false alarm. And that's typically, what we want to do for a radar system. All right, and here's my Lagrangian. If these are my distributions, you can easily write, the PD and the PFA in terms of this, this decision rule. I can rearrange these integrals so that it looks, in this way, which is simpler to interpret. And remember, phi can only take on one of two values. It's either a 0 or a 1. And so in this form, I can actually predict the optimal decision rule essentially by inspection. Since I want to maximize this integral, I just choose phi to be 1 when this difference is positive and to be 0 otherwise, right? And so this is the optimal decision rule attributed to Neiman and Pearson. If my distributions are well behaved and I can divide them, I can write this as a likelihood ratio test, right? So this is the optimal rule for detection for a radar system in isolation, all right? So this is just sort of basic review. All right, now what we want to do is we want to, sort of ask how well can we do when there's actually a comm system present in the same band as the radar. So let me make a comment on sort of the radar detection problem when there's actually a comms present. All right, so here's the geometry or environment I showed you before, right? Where it has my clutter and my interference, and I'm trying to go after my target. Now what we're saying is there are, these comm systems that are also present in my environment. And so they're going to be picked up on my antenna, my radar antenna at my radar. And so that's more energy that enters my band. But notice that there's a difference between the RF signature that I get from these comm signals versus the jammer. Right? The jammer I have no knowledge of at all. Right? It's just this barraging noise. They're not going to tell me what they're transmitting. That's, it's adversarial, right? Whereas the comm signals, they're cooperating with me. So I have some additional information about those comm signals. So I can exploit that to basically mitigate the interference introduced by the comms. And I'm also sharing my information with those comms so that they can mitigate my energy, right? And still accomplish what they want to accomplish.
Hey, Chris, I have a quick question.
Yes, please ask questions if you.
I probably missed this, but are you modeling the hostile jammer in some way, or?
Yes.
Okay.
Yes.
Where is that happening? Like, so in your hypothesis test?
Yes. So here's my binary hypothesis test.
Right.
This tilde has the jamming in it. It has the jamming, it has the clutter, it has everything else in it. And so typically we assume, as you'll see, that the data is complex Gaussian with some mean and some covariance. Typically we put the target in the mean and we let all the interference and jamming be basically characterized by the covariance of my distribution.
But I mean, like I can imagine that the clutter is Gaussian, but wouldn't the jamming, like if I was a jammer, I would try not to be Gaussian, right? Like I would try to be sort of, I don't know, like trying to fool you. So I mean, I guess like it's without specifying what the distribution is, it's probably hard to write down the hypothesis test. But is that, so for now, the assumption is that somehow we can Gaussianize the jamming for the sake of this discussion.
Yes,
Okay.
yes.
Okay.
Yes, no, that's a great point. I mean, and you know, if you have additional knowledge about the jammer, yes, you can exploit it.
Right.
And you know, I'll just tell you that there are certain programs where they do have that, and that's what they do.
Right.
So
Right.
I can't say any more than that, obviously. But if you know what your adversary may try to do,
Right.
and you can adapt your system to exploit, and that's exactly what we do.
Okay.
But you know, for this particular problem, what you said is exactly what I'm just going to assume everything is Gaussian.
Okay. Cool. Thanks.
Well, let me add to that question. So why can't we consider a robust detection framework to address these adversarial behaviors? Because that's where we don't know the knowledge of the clutter, right? Does the problem becomes more complicated with that setup?
I mean, you could argue that, you know, sort of, you know, what we do is robust in that sense, because I won't be able to go into details in this talk, but in an actual system, you know, we don't make any a priori knowledge about the, you know, sort of interference other than the fact, as Gautam said, that it's Gaussian,
okay,
right? But that interference, even if I assume it's Gaussian, I don't have knowledge of the actual covariance matrix. So I have to use the data to make inferences about what that covariance is. So in that sense, you could argue that the system is robust, right? And it does that adaptively over time.
Okay, thank you.
And maybe this is more suited for our post-talk kind of discussion, right? But there's a lot of recent work on doing hypothesis testing so what people have started calling robust is when not just so not only are you not allowed to assume a parametric family for your distortions, you're also typically gonna give it the worst case. Somehow it should be adversarial or heavy tailed or those kinds of things. And it turns out that it's all is not lost. Like there's still some interesting things that you can do. So yeah, it'll be interesting to see how that stuff meshes with what you're going to tell us about. But yeah, maybe we'll postpone this discussion to afterwards. Yeah, this is an interesting point. Yeah.
Yeah. So if you do have questions that you want me to clarify, please interrupt. I'm happy to answer. So here's the situation I have when there's actually a comms present, you know, in my environment, in my frequency band. So here's my comm signal, and it's present under both hypotheses, right? And so from the radar's perspective, my goal is still to find an optimal decision rule for detecting the target. That's basically my goal. Just tell me whether there's a target present or not. But in this situation, you know, because, you know, the comm signal is going to be transmitting continuously, you know, each time it's transmitting a different code word, the distribution changes. And so under each hypothesis, instead of having a single distribution, I have a whole class of distributions. And this is what we refer to as a composite hypothesis testing. There are various approaches to trying to address that. I'm going to look at both of these. The first I'm going to look at is the Bayesian approach, in which case you basically assume a distribution for the unknown parameters, which in this case are the code words of the comms from the perspective of the radar, and you integrate them out. All right, and that's something that's feasible here because I'm cooperating with the comms. So if I need to know the code book distribution, it'll just tell me, and I can just integrate it out and form a detector based on that. All right, so that's sort of the Bayesian approach, and it basically reduces the composite hypothesis testing back to a simple hypothesis testing, and then I can just form my likelihood ratio test, and I'm good. The other approach is generalized likelihood ratio test, and I'll say more about that when we get into sort of an actual system, and we'll introduce a more detailed model for the comms. All right, so let me say a little bit about, you know, the bound. And my goal here, you know, is basically to say, what is the limit on performance if I have a single comms and a single radar forced to work in the same frequency band, okay? But they're cooperating, so they share information. How well can they do? So we already know what the limits are in terms of communication data rate and rock performance when each system has the band all to itself. So we're just asking we're just asking what is the answer to that question when they don't have the band to themselves, but they're stepping on top of each other, but they're doing it in a smart way. All right. So I'm going to take some liberties here because my goal is really just to develop a useful bound. All right. We can ask questions about the practicality of this, but later. But right now, my goal is just what is the bound? I want to understand, what's driving it intrinsically. All right, so the way I'm going to do that, just assume that I have a comms and a radar, and I collected data over some period of time. Here's my radar data, here's my comms data. And then I'm just going to sort of stack them up into a single vector. So now I have a joint vector that has all the data from both systems. All right, and so you can think about this as the radar and comms as one big array, if you want. All right, if they're close together, then you can say it's a coherent array. If they're farther apart, maybe it's a distributed array. But you can think about it just conceptually as one big system, right? So I have both the comms and the radar in the same data observation. All right, and now I'm going to assume that I have some prior on whether or not the target is present or not. All right, this is my second liberty that I'm going to assume. Assume that I have these probabilities. All right, if I have those probabilities, I can use basic, probability theory to basically take those distributions I showed you on the previous slide, and I can basically just integrate over the priors for the target presence. And that will give me, the conditional distribution of my data given my code, right? And that's useful because I can use that to find the mutual information for the comms link, right? And if I wanted the, sort of just the prior or just the data distribution, marginal for the data distribution, I can integrate that over the code book, right? Now, with these two distributions, I can compute the mutual information. And that'll give me the optimal data rate, right? The comms is in there and the radar is in there, all right? So these two distributions will allow me to write down mutual information for a cooperative system that takes into account the presence of the comms and the radar, all right? And similarly, I can take those distributions on the previous slide I just showed you, and since I have the code book, I'm cooperating with the comms, I can integrate those over the code book, and that gives me P of X under each hypothesis. And I can use that distribution to write down a likelihood ratio test, which gives me the theoretical bound on target detection. Now, the thing that's nice about this is this is based on a total data observation. So if for example, the geometry between the radar and the comms is such that the radar is actually able to help the comms with its communication, that's represented here. Or if maybe the comms is positioned in such a way that it can actually help the radar, do target detection, that's represented here, right? Because I have this collective data observation that has both in it. All right, so now I can introduce this cooperative metric. And basically my approach is to, just sort of combine the two. You can think about this as a, sort of a generalized Lagrangian, right? Where the first accounts for what I want to accomplish with my radar, and the second accounts for what I want to accomplish with my comms. Okay? And so I can actually express this in terms of the distributions I just described to you. And what's interesting here is my goal is to optimize this cooperative metric over two quantities. The first is my decision rule for my radar, and the second is the coding distribution for my comms. All right, and if I express this out, notice that the decision rule for my radar only affects this first term, and so I can actually move this integral over the code book inside, and immediately I can recognize what the optimal decision rule is for the radar detector. Basically, the average likelihood ratio test. All right, so just using Bayesian integration, integrate out over the comms, and then form my likelihood ratio test. That gives me a theoretical bound on the rock performance of a radar cooperating with an impact comms. So, actually quite fundamental, right? And then if I have that rule, remember that my radar typically has a false alarm rate constraint. So what I would have to do is I would have to choose my threshold to satisfy my PFA constraint. And once I do that, I can plug the final decision rule back into my metric, and then I just minimize the result over the coding distribution for the comms. All right, so you know, and this isn't too bad. I mean, it looks complicated, but you know, even when you were talking about the capacity of a channel, there's no closed form solution in general for, you know, finding the optimal coding distribution for a comm system. It's a nonlinear search. I mean, there are algorithms like the Blake-Hood-Aramoto algorithm, which you can use to, you know, numerically efficiently compute those distributions, but still it's not closed form. You still have to do a search. So for this cooperative system, I'm just saying the final thing you have to optimize over is this cooperative risk. All right, and note that as I search over, you know, the coding distribution and I vary it, every time I vary it, I have to make sure I'm satisfying my PFA constraints, so I have to go back and readjust my threshold in general. But the framework allows me to basically find out what the optimal cooperation is. All right, so it's very fundamental, very basic. In fact, some of it may seem, you know, rather simple, but that's what we were after. We're looking for a very simple description for a theoretical, you know, limit on what's possible for cooperating systems. And so we apply this to sort of the obvious, you know, data model you might want to start with, which is the Gaussian channel. And if I were to write out the, you know, the ROC curve, turns out you can solve for it in closed form for that, that average likelihood ratio test that I just described. There it is, PD in terms of PFA. And notice here that it depends on what I've denoted here as SNR. This is your integrated SNR. Integrated SNR over the joint virtual array between the radar and the comms, right? It takes into account the noise and everything else. But that's what it is. And then the data rate for the comms turns out to be something that we can write down, you know, pretty easily as well. It's basically the capacity you would get for a, you know, a Gaussian channel, where KS is the covariance matrix for my channel code words, and KN is basically the covariance matrix for all of my noise, my interference, my clutter, my jamming, and so forth. All right, so all of that's represented there. And if I want to maximize this over, you know, arbitrary distributions, we know for a Gaussian channel that the optimal distribution is a Gaussian for the coding distribution, so that's already taken into account here. What's left is to optimize that distribution over the code word covariance matrix, KS. And those of you familiar with this know that the solution here is actually given by a water filling solution. All right, so it actually turns out to be, you know, basically the same form of the solution we had when trying to find the optimal rate for a Gaussian channel. But the interpretation here is really what's interesting. So remember that this covariance matrix is for the combined array for my radar and my comms, treating them as one giant array, right? And so in that combined array, there are these multiple dimensions in both space and time, right? And each one of those space-time dimensions represents a Gaussian channel, all right? And within that, in those channels, the clutter is going to fill up some fraction of those channels, the jamming is going to fill up some fraction of those channels, and the target I'm looking for may be in different pieces of each one of those channels, all right? And so in order to optimize the data rate, what the comms is going to do is it's going to pour its energy in the lowest power channel. So it's going to try to find the lowest noise channels, you know, that have the least clutter, the least jamming, and so forth, and start filling that channel with its, you know, power. There's a limited amount of power. It's going to start distributing that power in each one of those channels. And so as it does that, it increases its data rate. But what happens is as it starts, you know, water filling, what the radar sees is basically this effectively rising noise floor. Right? That's the way it appears in the radar's receiver. Right? And so we're positioned to basically plot this, you know, very nice, unique plot where I'm showing both radar performance and comms performance on the same plot. And so I'm showing on the vertical axis the probability of detection for my radar, and on the horizontal axis, I'm showing you the comms rate that I'm able to achieve. All right, bits per dimension. And this is for PFA of 10 to the minus 6, which is typical for a radar. And the SNRs that I'm showing you here are the integrated SNRs that the target has in the absence of a comm signal. All right, so that's at this point here. This point here is where those SNRs are valid. But as I increase the comms rate, these SNRs start to decrease. And eventually, you hit some sort of threshold effect where all of a sudden you get a very, very rapid decrease in detection performance. And of course, that's going to depend on how strong the target is. If I have a weaker target, you'll see that threshold occur earlier. If the target is much stronger, it has a little bit more robustness to the presence of the comms. All right, so this is sort of our result on the bound for a cooperative system, and it allows us to sort of understand sort of what the effective trade space is between the radar and the comms if they were actually cooperating in an optimal fashion. All right, so this is optimal detection, this is optimal communication rate, and in theory, you can't do any better than this. That's what we mean by it being bound. All right, so that's all I'm going to say on the performance bound. Now what I'd like to do is say something about the ROC performance. Right, now what I want to do is say, okay, if I'm going to design a system, you know, how am I going to design my radar receiver, and what is the probability of detection, say, versus SNR for a given false alarm? All right, and so let me just sort of give you sort of the big overview of how we're going to do this, and then I'll fill in the details. All right, so we're going to focus on a generalized likelihood ratio test receiver for, I think, the obvious reasons. It's usually a great place to start. It allows you to put in what you know and what you don't know, and the statistical theory is set up so that I can optimize over the parameters that I don't know, and it tells me the right way to compensate for that. All right, in the presence of a comms system. All right, and what we're going to do is we're going to use something called Wilks' theorem, which I'll describe in a minute, which is based on the Fisher information matrix associated with the Kremer-Albaum. All right, now that is going to be our approach, but there's still some obstacles. One of the obstacles is that the Wilks' theorem is only applicable when the parameters that you're talking about are continuous in your distribution. Because this is a cooperative comms problem, my comm system has symbols that come from a constellation of discrete, values, right? So all my parameters are not going to be continuous. I have a set of discrete parameters, so that's a roadblock. All right. The way we're going to get around that is we're going to use something called the constrained Kremer-Albaum. All right. So it allows us to start with parameters that are discrete, but when we impose these constraints, it allows us to deal with their discrete nature. All right. And we're going to use that as the basis for Wilks' theorem, and we're going to apply this to what the folks in the comms community calls the semi-blind constraint, in which case, when I'm transmitting data, some fraction of that data is going to consist of training symbols, right? Training symbols that we use to estimate the channel for the comms link. All right. So here's the problem. Here's the geometry I have. This is my radar receiver. All right. So each one of these dots represents an antenna on my radar, and there's a comms present. So in this case, we actually have multiple comm signals might be present. So these blue circles are my comm signals coming from different angles. All right, and each comms link has its own channel gain, which I'm denoting as alpha 1, alpha 2, all the way through alpha k. All right, and then, and this is for what we call a flat fading model for a communication channel. And then obviously there's going to be a return from the target I'm looking for as the radar. All right, and that's going to have some gain associated with it. And so the blue here represents my comm signal. The black is the additive noise, so that includes jamming and interference, clutter, and so forth. And then this green represents my return from my radar target. All right, and so for the comms component, I have a sum of signals, right? And so I have basically some steering vector for each one of my signals coming from a particular angle. Here's my channel gain alpha. and then here's my transmitted signal from the kth source. Okay, I should say the ith source, and there are k of those. And if I stack these steering vectors up into a matrix A, and then I let the alpha gains be collected in some vector, I can represent this sum as A times a diagonal matrix, which is what this delta alpha is, a diagonal matrix times my transmitted symbols. And then for my radar reflection, I have some complex amplitude times some Doppler times the spatial component. All right, and I'm going to make observations over some period of time, right? So I'm going to have some period of time, which I'm denoting here with t, going from 1 to n, and I'm going to collect all that data over that time period. And if you want, you can think about this as what we call in radar a coherent processing interval. Okay, and if I stack all of the data up, I can stack them all up into one vector. All right, and so there's a target contribution, there's a comms contribution, and then there's the noise. And notice that my complex amplitude multiplies all of these terms in my target steering vector. All right, and so now my hypothesis testing problem is based on the totality of all the data. All right, and now what I'm going to do is I'm going to assume that the data is Gaussian, and I'm going to assume that the covariance is given by R. So that characterizes my jamming, my clutter, interference, and so forth. And then my comm signal is present under both hypotheses at all times, and I'm just looking for my target. And I'm going to assume, for the sake of this analysis, that the covariance of my noise is known, and also that my target Doppler is known. And so if I collect all of the parameters that I have to deal with under each hypothesis, under the null hypothesis, I got to deal with all of these parameters associated with the comm signals. And then under the alternative hypothesis, I got to deal with all the parameters associated with the comm signals plus the radar target parameters. All right, so you see this problem is building up to be, complicated very, very quickly. And remember that the set of symbols that are transmitted by the comms are discrete parameters. All right, and everything else is continuous parameters. So we have to be cognizant of that and address that. All right, so let me describe the generalized likelihood ratio test. Before I do that, I want to make an observation here. Notice that radar detection is essentially, at its core, just trying to decide between two possibilities, whether or not that alpha t, which is a complex amplitude of my target echo, whether it's 0 or non-zero. Right, and I'm just reminding you of what my total data looks like. If this alpha is 0, there's no target present. But if it's non-zero, then I have a target present. So that's what we call an essential parameter. So it's going to be useful to partition the total parameters into two sets, a set of essential parameters and then everything else for the purpose of target detection. Everything else is what we call nuisance parameters. So that's going to include my, my comms parameters as well as my target angle, which is not really essential for detection. All right, and so the detection problem can be stated in the following way in terms of these partition parameters. Under H0, I'm trying to detect whether the essential parameter assumes a specific known value, all right, and under H1, whether it deviates from that value. So you can see this is once again a composite hypothesis testing problem. And the way we chose theta R, which I'm calling the essential parameters, is these are the set of parameters that have a distinct change under each hypothesis. All the other parameters will not necessarily change, all right, but there's a distinct change for this parameter theta R under both hypotheses. All right, and it's a composite hypothesis testing problem. Under the null hypothesis, I know with absolute certainty that alpha t is 0, right? And so I'm going to try to exploit that in my development of my generalized likelihood ratio test. So if you haven't seen the generalized likelihood ratio test, the basic approach is you form the optimal test, which is a likelihood ratio test, right? Which assumes that you know all the parameters. And then what you do is all the parameters that you don't know, you replace them with their maximum likelihood estimates. All right, and that's what we mean by the generalized likelihood ratio test. One of the motivations for doing that is maximum likelihood estimation has these wonderful convergence guarantees as you collect more and more data, or as you get higher and higher signal to noise ratio. All right, and sometimes we like to work in the log space, especially as we're dealing with complex Gaussian distributions. So the statistic that we're going to focus on here is this log likelihood ratio test statistic we replace the estimates with their ML estimators. All right, so just recall, here are my distributions, and I want to find the test under this assumption. All right, and I'm just reminding you of this, and then I'm just reminding you, here are my parameters. All right, some of them are discrete, and some of them are continuous. And so trying to find the statistic is very challenging. All right, so this is a highly nonlinear multivariate optimization. Right, some of the parameters are linear in the model, but a large number of them are nonlinear in the model. Some of the parameters are discrete, some of them are continuous. So you have a very, very complex statistic, a very, very complex function of the random data. So the notional idea of actually trying to find the PDF of this statistic and then using that PDF to find the raw curve is really daunting. And so most of the people that are working in this area, they just ignore this problem altogether, right? Because it's just really difficult. All right, so I just want you to have some sense of the appreciation for, the complexity of trying to do this, right? So it's a challenging problem. Most people are ignoring it. We want to try to make some headway here. And if you haven't seen Wilks' theorem, just sort of give you a quick description of what it does. It basically tries to leverage the asymptotic convergence of max likelihood. So here's my hypothesis test. Here's the generalized likelihood ratio test. Take the log of each distribution, and I replace each of my parameters with their max likelihood estimates. All right, but remember, under the null hypothesis, I know what the essential parameters are under the null hypothesis. Those alphas go to 0. So I don't have to estimate that. That I know exactly. But I do have to optimize over the nuisance parameters under H null. And what Wilks' theorem does is it uses sort of a second order approximation of Taylor series. And notice here that in the second order approximation, the matrix weighting this quadratic is the Fisher information matrix. All right, and this distribution at H1 is the same as that one by the chosen expansion, and so they cancel. And so what you're left with is this quadratic that involves essentially the Fisher information matrix for estimating the parameters. All right, and exploiting the convergence properties of max likelihood, you can show that this distribution is asymptotically chi-square distributed. All right, and this is and under the null hypothesis is non-central is a central chi-squared, and under the alternative hypothesis, when the target is there, it's non-central chi-squared, and here's its non-centrality parameter. Okay, now the beauty of this is that this statistic takes into account the statistical coupling between all of these parameters. That's an inherent property of Kremerau bounds. Okay, and so that's really attractive because what it does is it represents the intrinsic trade space, that's straight trade space that exists for this particular problem. The trade space that exists when the columns are stepping on the radar, when the radar is stepping on the columns. That's captured here. Right? That's a very, very important aspect, and probably the most attractive aspect of this distribution. Now, sort of the con here is that, well, it's asymptotic, right? Well, it's asymptotic, but it's better than nothing. I mean, without it, you don't have anything to say, right? Because the distribution is just really difficult to derive. But with this, we have a view into what's happening and what's possible for the radar receiver. All right, now the theorem that I just described assumes that the distribution is continuous in the distributions as well as being real in the parameters. All right, and that's not completely true for our problem altogether. So I'll tell you how we're going to get around that. To deal with the discrete parameters, we're going to use something called the constrained Kremerau bound. And the reason we can get away with that is because if you were to look at the asymptotic properties of max likelihood, when you constrain the parameters, you can show that it maintains those asymptotic properties of being both unbiased and efficient. And there's a paper there that actually goes through that process. So that's what gives us legitimacy for using the constrained Kremerau bound in Wilks' theorem. All right, so if you haven't seen the constrained Kremerau bound before, this is the unconstrained Kremerau bound that allows us to deal with complex parameters. This is a Slepian formula. We can just take our mean of our distribution, compute these gradients, plug it in, and we're golden. Right? We can compute the Fisher information matrix. Here's the form of it. This is very standard. We can plug it in and compute it. We're all set. To deal with the constraints, the way we deal with constraints is we introduce the constraints through these functions, F. All right, and I'll tell you how we're choosing them for the semi-blind training problem. But we basically have a set of functions that are set to 0. They represent our constraints on the parameter. We find a gradient, the gradient of those constraints with respect to our parameters, and that gives us this capital F function. And then we find the subspace that's orthogonal to the gradient of those constraints. This is just the way the bound works, and there's lots of references on this. Once I have that unitary matrix, I can modify the usual Kremerel bound in this way, and that gives me a bound on these parameters that takes into account these implicit constraints or these specific constraints. All right, and so then that's how I am able to compute my constrained Kremerel bound. And once I have that, I'm all set. So let me describe the semi-blind constraint. I'll show you some simulations, and then I'll wrap this up in a few minutes. So what we want to do is here's my radar receiver. We want to consider sort of comms links that are doing one of two possible things. You know, in a comms link, sometimes I'm sending training symbols because I don't know the channel gain, and I'm using those training symbols to estimate the unknown channel gain. When I actually know the channel gain, I don't have to estimate it, I can actually transmit data. All right, so those are the two modes of communication we want to represent here. And then, of course, there's possibly a target in my environment. That's what my radar is looking for. All right, so in terms of the constraints I'm looking at, I want to deal with training symbols. And if a comms is sending training symbols, the receiver knows what those training symbols are. All right, that's the point, is to know what they are. I exploit that knowledge to estimate the unknown channel gain. And so we can represent that by simply saying, hey, those symbols are equal to, the training symbols. And so that allows us to write the constraints in this form. All right. And then once we have those constraints, we worked out the matrix, the capital F matrix, there it is. And then the other thing we have to do when we deal with this other mode, we assume that the channel gain is known. We can just introduce a constraint on that second mode of communication that also looks very similar. I just say that the channel gain is known. In this case, we're setting the channel gains equal to 1 on this second comms. And then from that, we can compute the capital F matrix, and then we can combine them into one matrix, find a unitary transformation, plug it into our bound, and we're good to go. All right, so once I have that constrained Kremerel bound, I can find the part that corresponds to my essential parameters, in this case, alpha. And as I said, everything was complex, but we can use this simple transformation that takes the complexified Fisher information matrix and converts it to a real Fisher information matrix. So that's what we've done. There's a reference there if you're curious as to how that's done. But we can do that. We can map it into an equivalent set of real parameters, and then we can just use this in Wilks' theorem to compute basically the log performance of the GORT. Okay, so let me just show you some results. Here's an example where I have two comm signals and a target in my environment that my radar is observing. My two comm signals, one is at broadside, 0 degrees, and the other one's at 5 degrees. One is actually in the mode of training, and the other one's actually communicating real data. All right, and they have a SNR of 10 dB on each link. For the comm signal, I'm assuming additive white Gaussian noise, but this theoretical framework is general enough that we can actually introduce some high fidelity modeling later on. But for now, we're going to assume that this is additive white Gaussian noise. And then here are my gains that I'm assuming for each one of my channels. And because of the modes of communication, alpha 1 I'm assuming is unknown. That's why I'm sending training symbols. Alpha 2 I actually assume that I do know, and it's actually sending or communicating actual data. For my target, I'm assuming that's at 30 degrees off of broadside, and I have an SNR of 40 dB. And once again, I'm assuming my target Doppler is known. I'm just going to put it at 0 dB. And I have a 5 sensor uniform linear array. All right, so first I'm going to compute the Kremerel bound on the angle estimates for the comm signals. All right, so Kremerel bound on estimating phi1 and phi2, I'm showing you here, but I'm showing you the bounds on these estimates as the data is coming in. all right? And I'm sending training data on link 1, each time. So this bound is based only on the data up to time t. So I'm showing you what the bound is. You can see that I'm doing better as I continue to increase or collect more data, which has the training in it. I'm able to estimate the gain on the first link and then subtract that off to go after the angle on the second. And then I can subtract both of those off to go after the target eventually. And the other thing we can do is we can say, okay, I've collected all of the data over that time window, and only a fraction of those samples actually have training symbols. This is the semi-blind constraint, right? And I can use the Crumerel bound to tell me how well I'm able to do there. And so on the first signal, the comps link, I have a performance that doesn't change much at all, but on the second link, I get better performance as I continue to increase the amount of training, the fraction of training that I have in these total 100 observations. All right, and then here's just a plot of those on the same curve. And I'll just tell you that these results that I'm showing you here for this comms link, this is a scenario that was presented by Brian Sadler and his colleagues. And so what we did is we took their results and we stuck a radar target in there to represent the comms signal or the radar signal to see how this cooperative system behaves. And the curves that we're showing you here are almost identical to Sadler's results. So according to this result, the comms is almost, not affected by the radar at all. And so that's a good thing, but it's not affected at all. We're getting exactly the same curve. Now we can use Wilks' theorem to predict how well the radar is able to detect the target. And this is our result. So we're able to show you probability of detection versus the element level SNR for different probabilities of false alarm. And I'll just tell you that the range of PD versus SNR that you're seeing here is actually quite typical for a radar system. So this is what we're able to compute using Wilks' theorem. And I couldn't resist comparing, one of these curves to what I would have gotten if the radar had the full band to itself. All right, and so this blue curve is the radar cooperating with the comms, which is one of the curves I just showed you, and I'm just showing you for PFA of 10 to the minus 6. If I were to plot the same curve, if the radar had the full band to itself, that's this red curve. And so we're actually able to show you what the loss is when the radar is actually forced to play in the same sandbox with the comms. It introduces effectively a 2 dB loss, which from a practical perspective is actually quite good. So we're able to, operate with the comms without affecting the radar performance much at all. And that 2 dB is something we can make up, in the system very easily by integrating longer or, changing parameters somewhere else in the system. So we're pretty excited about that. The theoretical framework that I just provided you in terms of predicting performance has broad utility. We just sort of demonstrated it on a very, very simple example, but all the knobs are there to basically introduce some very, very high fidelity modeling and different types of modulation schemes for the communication system. So we can explore a very, very complicated trade space and say some very significant things about what's possible in terms of a radar receiver. So we're pretty excited about this. And we also have, as I said, this cooperative bound, which basically lets me, predict what's possible if you did everything right, in terms of a comm system and a radar system working together. So I think with that, I'll stop and open the floor for questions.
All right. Thank you, Chris. That was a great talk. I guess we Zoom clap. I guess I don't know how to do that. Wait.
Let me also say, if anybody finds this interesting and they want to pursue, more details, we have a couple of recent papers. The last results I just showed you, we presented in the radar conference last month. This is work done by my PhD students, Tosif Ali and Akshay Bandre. So we have a paper on that, and we're in the process of actually generalizing this to include modeling errors, modeling specifications. So we have another paper coming out next year on that. And we're in the process of writing a full paper on this topic. But pretty excited about these results because, as I said, up to now, everybody's been ignoring this part of the problem.
Very cool. Are there other questions? Akshay and Tosif are also here, so you can bug all three of them simultaneously. Questions? Okay, I'll go first, and then maybe. So, is there any sense as to how bad things can get if there is no cooperation between the comms and the radar? Is there a way that you can, I mean, let's say they're not adversarial. Let's say each are doing their own thing. You just have to maybe detect what the comms is doing while doing the radar, and the comms detects what the radar is doing while doing the comms. Is there, can you prove something like a benign degradation?
Sure. Basically, the way that, I mean, what happens when you treat it that way is that the comms just becomes like any other jammer.
Right.
It's just like another jammer. And most of these radar systems are equipped to deal with potential jammers. So when you're treating it as a jammer, I just remind you, and you don't have any information and you're not cooperating, then it becomes a little bit harder. It's not that you can't do it, but it becomes a little bit harder, and you're not able to exploit any prior information.
Mm-hmm.
And so you may end up with performance that's acceptable, maybe only under certain regions. But sort of assessing performance of a radar system in the presence of jammers is something we've been doing for decades.
Mm-hmm.
Particularly jammers that are not our friends. They're not helping us out. We don't know what they're transmitting, and they're very clever at moving things around. So that basically just reduces it to the problem we've been dealing with for decades. So what's unique about this problem is that we are cooperating and we're working together to basically counter each other's mutual interference.
Okay. I mean, is there so it should be easy to simulate like the performance when you treat the same radar as the same comm system as a jammer, and the same comm system using this approach, and see what the loss is, right? Like, is there, instead of 2 dB?
Yeah, that's a great point. That's a great point. So you could actually quantify the gain from cooperation.
Right, exactly. And in fact, it'll be nice if we can also show that theoretically, but at least you can show a curve that shows like how much the rock curve moves, right? Essentially.
I actually really like that idea. So if you don't mind, I'll borrow that. But I actually like that idea. Sort of quantifying the benefit of cooperation.
Right.
I think that's a great idea. In fact, you could use that to sort of sell why you would want to cooperate when it's possible.
Exactly.
So I had a question, Chris.
Sure.
So I apologize if you talked about this and I missed it, but so you were talking about how one of the difficulties with the sort of accounting for the communication system is that it's discrete, but of course, like the communication is designed to be easy to recover on the other end, right? Mm-hmm. Not by the radar, but by the receiver. So does that also help with like solving this problem?
Absolutely. Yeah. So it is going to be, it's going to be just as easy for the radar to decode, to demodulate and decode the comms as it is for the comms receiver, right? Because we're sharing information. So I know the code book, I know the modulation scheme. That's all been given to me by the comm system. And in fact, if you were to just sort of like dissect the GLRT, like just sort of peel back the layers, it's literally telling you to do that. It's basically saying, demodulate, decode the comms, subtract it out, and then go after the target. That's basically what it's telling you to do. But it's kind of nice to see that emerged out of sort of a GLRT formulation.
Right,
but that's only possible. It's only possible, to do what you said, to sort of do it easily if that information's been shared with me. If it's not shared with me, then I have to reduce to, sort of the question that Gautam asked, which is, I don't know anything about it. I got to treat it like any other jammer unless I have some additional side information somewhere else. But it's the cooperation that allows me to do it with ease. But the discrete nature of it was a it's an impediment if you're trying to quantify performance. And I know you know this really well, but it was a long time before we even got our arms around how to predict the bit error rate for a maximum likelihood decoder. And to my knowledge, that's still an open problem. I think that the most useful result is Gallagher's bound, right? I mean, it's in his textbook, but it's a bound, but it's probably one of the nicest bounds on that problem. But it's a non-trivial thing just to predict the bit error rate on the columns. So now I have a system where I not only got to deal with the maximum likelihood decoder in the comms, now I got to tell you what the distribution of the detection statistic is that's relying on that demodulation and decoding of the comms. That's a hard problem. So, which is why everybody's been avoiding it, which is why I'm pretty excited about this result, because we're applying, a Wilks theorem to this problem that basically allows us to say something about what you can expect. And, I spent, 20 years at Lincoln. This is the kind of thing that we can really use when you're designing systems, right? Because the sponsor comes to you and say, I need to detect a target in this environment under these conditions. And oh, by the way, over here, there's a lot of people that are probably going to see us. They're going to know you're there, and they're going to cause you a lot of problems, right? And they're giving us a lot of money to basically design a system that can give them that capability. And I want to be able to say, yeah, you can do this, but I need to be able to predict performance. So if you study radar detection theory, a large percentage of the papers that are published are on characterizing the rock performance of a radar receiver. And so we want to be able to do that within this shared spectrum environment, but it's very difficult, as I tried to, sort of convey. But this theorem actually gives us a glimpse into basically the intrinsic trade space that governs that rock.
So, Chris, did what you said a minute ago suggest that the clean algorithm is motivated by, or can be motivated by, doing GLRT in stages?
Yes. Yes. Oh, okay. Yeah, and it's kind of nice that it works out that way. In fact, most people that started looking at this problem early on, without trying to do the GLRT, that's just sort of my first initial ground zero approach. But if you didn't even think to do the GLRT, the obvious thing is, just decode it and then subtract it off. And in fact, that goes by a name. I think people call it SIC, S-I-C, Signal Interference Cancellation Receiver. Yeah. And so that's basically what people have been doing. But I kind of wanted to formulate it within a detection framework and say, hey, what would the traditional GLRT approach tell me to do? But when you look at what the math is saying, it's saying, decode it, subtract it out, and go after the target.
Yeah, that's interesting. I mean, of course, I knew that was done in a number of contexts, but I don't think I've ever seen it written down where it was derived from a information or detection theoretic point of view.
So the other thing that's interesting here is, I just characterized the rock performance of the GLRT, and I have to admit that we haven't even derived the GLRT yet. No. It turns out you can use this theorem. I've kind of put that challenge on my graduate students so they know it's on our to-do list. But I know already that there are at least K+1 parameters that are non-linearly related to the model. So you're never going to be able to write the statistic down in closed form. The parameters that are linear in the model, you'll be able to work those out in closed form usually. Then there's going to be a part of that statistic that just says, find the max over these parameters. Right? I mean, that's how you write down the statistic. Max over these angles and this dot. There's no closed form expression. So, it's always going to be a final optimization that you have to deal with. And so trying to find the distribution of such mathematical form, this is difficult. It's difficult. So this theorem actually really allows us to make some headway. And of course, we're exploiting stochastic convergence. That's the typical way, to make headway is you exploit stochastic convergence. And that's what we're doing.
So the Wilks theorem itself does not need any assumptions on the distribution, right? It just works.
Exactly. That's right. Even though we assume that the data distribution is Gaussian, that theorem is true whether it's a non-Gaussian or Gaussian distribution.
Right.
And the reason that's true is because, as you see, the final form is just this quadratic involving the maximum likelihood estimates. And the convergence guarantees of maximum likelihood estimates is that they're Gaussian.
Right.
Regardless of the underlying distribution, right? So that's what we're exploiting.
You mean to say chi-square, right?
Well, the maximum likelihood estimates are Gaussian. And then when you put them in that quadratic form, you end up with a chi-square.
Right. I have a question related to your cooperative risk formula. Can you go to that slide? I think slide 6 or something, I don't remember.
Sure.
It's the slide early after the deduction itself.
So this one?
Yeah, so how did you get that equation, the top equation? Did you propose that metric, or it's something that comes from some derivation?
No, this is something I proposed.
Okay.
And the reason I proposed this is that when I got brought on this program, this is sort of my last few years at Lincoln. It was a DARPA program called Spark, and I looked at some of the approaches that people were taking, and they basically fell into two categories, two obvious categories. The folks that were comms experts basically came in the room and said, "Oh, I can treat the radar like a comms. It's just like another interfering comms." And that's what they did. So then when the radar folks would come in the room, it's okay, well, what's the probability of detection? And they go, "Oh, I don't know. What's the parameter estimation law? Oh, I don't know." And then the radar guys came in the room and said, "Oh, comms is just another jammer. I'll just treat it like another jammer." So, is that the optimal cooperative? Oh, I don't know. So I wanted a metric that would allow both communities to talk to each other, number one. And number two, a metric that tells me explicitly what the PD, probability of detection, is for the radar and the data rate is for the comms. I don't have to guess. I don't have to do any transformations. I'm not waving my hands. There it is. And so what I did is I just took both metrics that have legacy in both communities, and I just took a linear combination of them, where the coefficient here is just gamma. Effectively, this is just a Lagrangian, right? So, and then I said, let me just optimize this Lagrangian over both systems. And so this was part of our contribution. As far as I know, we were the first to propose such a metric. And so then the question was, okay, how do I optimize this? And because these are, some of this was, as I said, similar enough to the original problem when you're dealing with the systems in isolation, I was able to make a little bit.
And in the subsequent slides, thank you for the answer, thank you. And in the subsequent slides, you also have an upper bound on the channel capacity, right?
Yes.
Yeah, so the C. So what is NS? There's the total number of bits there.
So I'm sorry, what's your question?
In the last part of that summation, it's until NS, right? So that's the number of samples, or?
Oh, NS is, that is, very good question. That is basically that's the number of Gaussian channels. It's the number of Gaussian channels. So this is actually a standard formula. If you've ever, studied information theory, basically the capacity of a Gaussian channel is obtained, particularly when you're dealing with colored noise, is obtained through water filling. And so all I'm doing is writing down the effective SNR in each dimension of that space.
So this SNR is different from SINR you have in the square root?
Yes, it's different from the SNR I have in the square root. That's right.
The reason I'm asking is that because in the infinite case, this summation typically admits an asymptotic version, right? I mean, it involves this channel capacity for Gaussian in the asymptotic limit. I don't remember the name. It's an integral over log 1 plus HH transpose, something like that. So that's the reason I asked.
Okay. Yeah, this SNR, that's a good observation. This SNR is basically the effective SNR within each dimension. And remember, my dimension is obtained, generally speaking, as a joint space-time dimension, right? I have two receivers. I have a radar receiver and I have a comms receiver, and I've collected data over the same time period over both receivers. And then I've stacked them up into one vector. And the covariance of that vector is what I am representing here by Ks plus Kn. And once I do an eigen decomposition in that space, I get these Gaussian channels. And so in each Gaussian channel, there's an effective SNR. That's what this SNR sub SI is.
Yeah, usually this is finite dimensional. I don't know how to do Shannon capacity for an infinite dimensional channel, but
I remember vaguely from Robert's Gray-Wood circular matrices. I just remember from that. I'm familiar with that expression. That's the reason I'm asked. Maybe a stupid question, but I just wanted to ask after everyone left.
I think that's an interesting question. I think usually the way that's done, if you want to deal with an infinite dimensional channel, so that you actually have a continuous waveform. Typically, the way that's done is you basically, model both of these, say, as stochastic processes, and then you assume a set of basis functions, and you project basically those time series onto each basis function, and that projection gives you a random variable, right? It gives you a random variable that puts it back into this sort of vector space. Right? This is the way it's sort of described in Gallagher's book, and how you're actually able to, write down Shannon's very famous formula that gives you the capacity over a band-limited channel. Right? It's a continuous waveform, but this is how they deal with the infinite dimensions. They basically assume a set of basis functions. And these are continuous functions, and then you project each of those received data onto these basis functions, and that gives you a coefficient. And it turns out that coefficient now assumes the Gaussian distributions that we're talking about. So it goes from being a continuous infinite dimensional problem back to a vector finite dimensional problem. But
sorry.
I'm sorry?
Yeah, go ahead. Sorry to
interrupt you. No, what I'm saying is the result is basically that formula that Shannon is probably most recognized for, which is that band-limited, the capacity over band-limited channel. You take that vector formulation, and then you divide by the duration over which you're observing the data, and in the limit as t approaches infinity, or I should say, not even in the limit as t approaches infinity. Basically, you can leave that in there, and you'll end up with effectively that band-limited formula, or the capacity for a band-limited channel, which is the bandwidth times log of 1 plus the SNR, or something to that effect. But effectively, you're dealing with an infinite dimensional problem in that case, because you're talking about continuous waveforms.
So finally, in the second inequality here, you have this determinant of Ks plus Kn divided by determinant of Kn, right? But in your hypothesis framework, the signal or the communication system is present in both the hypothesis, right?
Yes. Very good observation. Very good observation. So let me show you why this is correct. So that's correct. So under the null hypothesis, you don't have any problem, right? Because the target's not there, right? But the target is represented in the mean of the distribution. So remember, mutual information is the entropy minus, say, the entropy of my data minus the entropy of my data conditioned on y, right? And if they're both Gaussian, if there's something in the mean of the distribution, it's invariant. The entropy is invariant to that mean. So it never even shows up in the data right here.
So can you go to the hypothesis framework? Sorry.
Sure.
Yeah, so here you have S tilde R in both, right?
Yes.
In the both, so I'm thinking that that distribution is zero mean and KS. Is it not the case? And
yeah, so the distribution of the data under the null hypothesis is zero mean Gaussian with a covariance of Ks plus Kn.
uh-huh.
And I have to be careful here because remember, this is just the radar data, but the Ks and Kn is what I get when I stack this XR on top of XC, right?
Right.
So if you're okay with following that, then under the null hypothesis, the covariance of that total data is Ks plus Kn. I'm assuming that the coding distribution is Gaussian because it's about, for Gaussian channels, the optimal distribution among all distributions is a Gaussian one. So that's why we don't have to max over the covariance of the coding distribution, right? Now, under the H1 hypothesis, even if I were to compute the mutual information, this term would never even affect the distribution because it's in the mean of the distribution.
But still you will have Ks plus Kn, right, in H1 as well.
Yes, you will still have Ks plus Kn, that's right.
Yeah, so
this formula here is not because of the two hypotheses.
Okay, that's the question.
Yeah, this is a standard formula. This is the capacity of a Gaussian channel.
I see. But yeah.
The communication part.
Okay, so if you write for the detection probability, then we will get divided by the determinants being the same, right? That's the reason I was asking the question.
I'm sorry, say that one more time.
If you write the probability of detection in the likelihood ratio test, then the covariance under numerator and denominator will have the same kind of determinants because the covariance is same in H0 and H1.
That's exactly right. That's exactly right.
Yeah. So, but here in this case, we are dealing with information case, so we don't see that kind of cancellation.
Right. Well, this formula has nothing to do with H0 and H1.
Okay.
That's what I'm trying to tell you. If you open Cover's book and you look at the expression for the capacity of a Gaussian channel, this is the expression.
Oh, okay. Okay. So it's just dealing with one capacity channel. Okay.
Yeah.
Makes sense.
Yeah.
Okay.
Yeah.
Yeah. Thank you. Thank you so much for answering my questions patiently.
Thank you for your questions. Yeah, no problem.
Cool. Are there other questions? So Cover's co-author Joy Thomas, he recently passed away. Apparently, I just found out a couple days ago. I mean, or a week ago or something. I think he went on to become an engineer of some sort.
You talking about Thomas? You talking about Cover? Or you talking about Thomas?
Thomas, yeah. Cover passed away a while ago, right? But,
oh, okay. I didn't know that.
Yeah. Thomas passed away like just recently. I mean, maybe a month ago.
September 28th. That's what Wiki says.
Yeah.
Oh wow! I didn't know that. Because I actually, when I taught, I was going to teach information theory at Harvard for the first time in 2014. I sent Thomas an email because I knew Cover had passed away, and I asked him a question. And anyway, he responded, gave me the information I needed. So I'm really surprised to hear that he passed away. I thought he was seems like a pretty young guy, wasn't he?
Yeah, I thought so as well. Like I think.
Yeah, it says 57 years old. So.
Yeah, that's young. Wow.
Yeah.
Sorry to hear that.
I think he's so he was a senior data scientist at Google, I think, when he passed.
Oh, okay. Wow.
Anyway, that book essentially made information theory accessible.
Oh yeah, it's like it's definitely the student's choice. Like that's like the #1 used reference.
Yeah, we did in Wisconsin. Like we did a reading group on the Shizar and Kerner book.
Yeah.
It was insane. I think
it is insane.
I think it aged me by a couple of years in that one semester.
We did a reading group here a few years ago using Kinchin's little pink pamphlet.
Oh yeah.
I have that.
The students were saying, well, what are we going to do after we're through with this? I mean, this can't take more than 3-4 weeks. And it kicked everyone's can.
Right.
I'm actually, I would volunteer my students some of them are here, for a reading group if we can decide something that's interesting and hardcore. I think it'll be fun to bang our heads against it, or get our students to bang their heads against the wall, and then
That's different, slightly different.
Yeah. So yeah, I'll be open to that. It'll be fun. But yeah, thanks, Chris. This was amazing. Thanks for all the patiently answering all questions and giving us a talk. I think we have taken up enough of your time, and yeah. So see you all next week. We have I guess only friends here, but essentially we have an external speaker. This guy actually went to school with me. He's my academic sibling, and he's at UWash. He does some cool online machine learning kind of stuff. So he's going to be talking on next week. Yeah. So we'll look out for the emails, and see you folks next week.
All right, thanks, Scott. Appreciate
Good to see you. Good to see you, Chris.
You too, Doug.
See you later.